So, good morning. Welcome to Krishna's classroom. We continue with our discussions on the implicit function theorem. In this talk, we look at some applications. We already completed the proof of the theorem and discussed it in detail. It's appropriate that we look at some examples to get a feeling for how it is applied. So, we look at the example. So, we take the case of F is a map from R5 to R. R5 to R. Okay, so f is given by, it's a vector valued function, so f is equal to where f1 of y3 is defined by 2 e power x1 plus x2 y1 minus 4y2 plus 2 f2 of x1 y3. Now you see that this I rewrite in the form f is a map from R to cross 2 Let us consider the points A belonging to A equal to 0, 1, B So let us take x equal to then what we have is, then we observe that f of 0, that is f1 of zero. Now look at f dash f derivative at AB is a linear transformation from R5 to R2. And this can be written as, so the matrix representation for f derivative AB define it as A. This is equal to this is given by the 2 by 5 matrix 2, 3, 1, minus 4, 0, minus 6, 1, 2, 0, minus 1. Now this comes from the following. That is, you have got df1 by dx1, df1 by dx2, df1 by dy1, df by 1 by dy2, df1 by dy3, all evaluated at the point AB. Similarly, this is df2 by dx1, df2 by dx2, df2 by dy1, df2 by dy2, df2 by dy3, all evaluated at the point AB. So just verify that this is true. Now this I can just put a dash here to break it up. So Ax is equal to, now this is with respect to the ordered basis, the usual standard basis that you use for R5 and R2. Okay. Now Ax is equal to now we have Ax inverse equal to, that is what you say, this Ax is invertible. You just check the determinant of Ax to see that it is not equal to 0, and what you have is this Ax inverse is equal to put it this way, 1 upon 20 my, okay, (1 minus 3 6 2). That is Ax inverse. Now what you can assert is the following. Since at AB, okay, A is given by this and the corresponding Ax is not equal to, is invertible, there exists and an open set W contained in R3 with AB belonging to U and B belonging to W, such that for every belonging to W, there exists X belonging to unique X such that X is equal to XY belongs to U and F of 0, and if X is denoted by G of Y, X the corresponding X. F of equal to 0 for every Y belonging to okay. And for this particular function, see that for this G, G is of course smooth, since F is smooth, and the derivative of G is given by G2. Then G derivative is given by, at AB is given by equal to 1 by 4 equal to 1 upon 5 3 by 20. Then dg2 by dy1 equal to minus 1 by 2 1 by 2. At seven, and what you have is this, that is f of gyy equal to 0 for every y belonging to W. Now this is the application of the implicit function theorem. That means fxy equal to 0 can be solved for x as a function of y in some neighborhood of the point B. Okay, and this is the, and what you get is f of gyy equal to 0. So that's the application of the first, that gives an application of the theorem. Now we take up another example. Second example. Which can be solved by, with the help of the implicit function theorem. Let us consider the following problem. Example 2. nonlinear system of equations. Equal to 0. So we rewrite this in the form. Okay, we take up. So the question that you are asking is this. The first question that we take up is this. See, this is a nonlinear equation merely because of this term. Otherwise, it becomes a linear equation. Okay. So if you were to solve 3x plus y minus z equal to u square, x minus y plus 2z is equal to u, 2x plus 2y minus 3z is equal to minus 2u. If these equations are to be solved, then of course it's a question of very simple. It's just solving the linear equations. Okay. So this is a function given on this side, and you can easily solve it. I mean, solve it or not solve it. I mean, that depends on the coefficients that appear here. We will examine this also. So otherwise, suppose you have to solve this for x, y, and u in terms of z, say, or x, z, and u in terms of y, or y, z, and u in terms of x, then you are working on a nonlinear system. Okay. So the question is this: does there exist a solution for x, y, u in terms of z? This is the question that you are asking. Okay, this is the question that we are taking up. So what we do is we rewrite the whole thing, we reshuffle the terms and rewrite the whole thing in the following form. So let us rewrite or this system as two x plus 2y equals 0. Now you write this as a map from, okay, so you write this as a map. So let us take belonging to R3 and Y as now set x minus y two x plus 2y plus 2u minus 3z minus 3z. Okay. So let xy, that is f is a map from so now you see that f derivative of xy, this is equal to, this is a 3/4 matrix given by 1 2u then minus 1 1 minus 1 1 2 2 2 2 minus 3. Again I just put a bar. Let me just designate this by u. Then you have got ax. And one observes that determinant of, compute this, determinant of ax equal to h and ax is three by two, not equal to 3 by 2, u not equal to 3 by 2. Now we take, so let So this is the crucial identification. So we take x naught equal to then x naught R4, and we have the condition that u naught is not equal to 3 by 2 by our stipulation, and you see that by the implicit, then we apply the implicit function. By the implicit function theorem, there exists U open in R4 it's an open neighborhood of x naught it's an open neighborhood of x naught, y naught, and R1 a neighborhood of y naught such that, see, what we can say is that for every y belonging to a unique x such that x y belongs to u, and f of equal to c. This is something that you can say, and because of this identification of a unique x corresponding to y, we can write because of this identification, that is corresponding to every y belonging to w, there is a unique x determinant. Therefore, what you have? You have x is equal to a function with domain W such that x is equal to gy and f of gy equal to 0. Okay, and then of course you have statements about all this, and further we have x naught is equal to g. And therefore, what does it say? It says corresponding to each y there is a unique x, or in other words, you can solve the given set of equations given y, you can solve it uniquely as x for x, y and z in some neighborhood of the point x naught, y naught. Okay, that's what it means. Thus, the given equation can be solved for x is equal to x y u for y thus for any choice of y there is a corresponding x y u, and by the condition that f of gy y is equal to 0 or f of xy is equal to 0, it assures that this is not equal to that this condition, this will not occur. So in the x y u that you solve for a given y, there is a unique solution and u will not be equal to 3 by 2. Okay, so this uses the implicit function theorem to assert that for a given y, for a given y, capital Y, that means corresponding to a given z, small z, there is a unique solution for this equation. Okay, so that answers the first question. Now the second and third question can be answered in the same way, and you can see that the question 2 is, does in terms of y for the equation f1 of this is the question that you have. Once again, what you do is you completely repeat the same procedure, except that now all that you need is you take x equal to xzu and y equal to, this is all the difference that you have. Then you have f of equal to 0. Now this amounts to just a reshuffling of the columns of the equation, okay, and then completely following the same arguments, and that will give you an application of the theorem. In fact, you see that the x, y, so corresponding to every y there exists a uniquely determined x in some neighborhood of the point x naught, y naught, where of course you have the condition that the corresponding ax is not equal to 0. Okay, so this has a solution, and the situation that comes out to be that would mean that u is not equal to 3/2. Sorry, I think, yeah. Once again, if you take up the third question is for the same problem. Exists solution for yzu in terms of now this is again possible because you can use the same argument. The only thing that you have to do is to choose the capital X and capital Y appropriately. So okay. Once again, we choose. Now we choose x equal to and y equal to and rework on the equation accordingly. And then you see that, of course, here also you will see that the corresponding Ax not equal to 0 would correspond to u not equal to 3 by 2. Once again, the same arguments follow. That is a function with domain W, say g, such that x is equal to gy and f of gy y equal to 0 with x naught equal to gy naught, and that is as you have in the part 1. But now we ask the next possibility. A solution for now what do you do? In this case, you choose x is equal to y equal to u. Now Ax in this case is the matrix 3, 1, minus 1, 1, minus 1, 2, and 2, 2, minus 2. And you can see that determinant of so this in turn tells you that the nonlinear equation cannot be solved for x, y, z in terms of u. That is, Ax is not invertible. So this is the scenario that you have. So in 3 situations we can do it, whereas in the 4th situation that we are not able to do this. So these are the questions. The pertinent questions are this one question, and of course you have a third question, or the 4th question is this. The answer to this is no. I think that completes that part. Now we will look at another situation where you come across the necessity to apply the theorem. And this is a situation that you come across in the context of differential equations. Okay. Where we straight away apply this result and then reduce the equation to a what you call a normal form, and there you can develop the theory for that. Okay, so let us work on this. So the problem is this. So consider ordinary differential equation given in the general form where x is an independent variable y is the dependent variable and y derivative so it's a relation connecting the independent variable, the dependent variable and its first derivative. This is the most general form. Now let us consider the following. Let f be defined from some omega to be a real valued function. Let us assume that f C1 function. In fact, to work the theorems, all that we need to assume is that f is C1 with respect to the third variable. So this is what you have. So for it's a real valued function, and we also assume x naught, y naught, z naught equal to 0 and df by not equal to 0. So in omega we are assuming that x naught, y naught, z naught is a point such that f of x naught, y naught, z naught equal to 0 and df by dz at x naught, y naught, z naught is not equal to 0. Okay. Then we can immediately apply, this implies the following. We are applying the implicit function theorem. So you write this in the form, in this particular form. That means you write this as f of zero, where x is equal to then f is a map from R3 to R. Okay, and then you see that f y, so is at not equal to 0. That means Fy is invertible. The meaning of this is that Fy is invertible. This is invertible. What is the consequence? Now applying the implicit function theorem, therefore now we can apply F now what could one say? There exists R3 and W R2 such that for every y belonging to W there exists a z belonging to R such that x, y, u and z is equal to g of xy. Okay. Consequently, further we have z naught equal to g of y naught f of xy is equal to 0. This is the consequence of application of the implicit function theorem. Okay. Now let us see what is the consequence of that. So now we look at this one, f of x zero. Now the question that you have is this. Given x naught, y naught, and z naught equal to 0. Yes, there exists a function y of x belonging to some interval I, x naught belongs to I is an open interval. Such that f of and f of x, y derivative of x equal to 0. This is the question that you have. This is the question that leads to the existence theorem. And this x naught, y naught turns out to be the initial data. And y naught, z naught is automatically fixed because of the condition that f of x naught, y naught, z naught is equal to 0. Z naught cannot be arbitrary because z naught is bound by the condition that f of x naught, y naught, z naught equal to 0. X naught and y naught you can fix in such a way that this x naught, y naught, z naught would happen to be in the domain of f. Okay. That means what? This is equivalent to the following question. Okay. So this given equation has a solution if and only if see, this equation can now be replaced by the following. this problem is equivalent to the first order equation in the normal form y derivative equal to f of xy, sorry, g of xy, where of course if xy belonging to the particular w that we have identified. Okay, and every solution of, see, because for given z, g of xy is xy is uniquely defined, so that defines a function z is equal to g of xy. It's clear that these two are equivalent. Hence, while the first order equation in the normal form. That's why the general theory is often working on this particular equation, and this is the normal form. So instead of working on this, one works on this. That is because by an application of the implicit function theorem, you can show that these two are equivalent. Now there are many places where possibly one can apply the implicit function theorem. So let me stop this with that. So thank you very much. Okay.